Hello, everyone. This week, we will talk about energy, environment, and human health. Some analytic questions if we talk about after this session that we were able to address, such as what are the environmental impacts of a fossil fuel power plant, for example. And with the emission rates, technology characteristics, and evolution of the pollution control, we should be able to do some calculations or simulations of the emissions of certain power plants. How much water would you save if you replace all water cooling plants with air cooling, water consumptions or water withdrawal, important water impact of our energy systems. And this it gives example of a power plant cooling practices. And air cooling has very important implications on water consumption, especially in locations that water scarcity is a big concern. Other questions such as what are the human health impacts of energy is mostly related to the links between energy use and air pollution and human explosion to air pollution that create health problems. What are the co-benefits of energy transitions? When we move from fossil fuel energy system to more renewable-based energy system, it has co-benefits such as reducing air pollution, reduce our water consumption, and reduce the impacts to human health. So those impacts are our co-benefits of energy transitions. We used this chart at the very beginning of our class to show the complexity and the system between energy demand and energy supply and different technologies and different stage of a conversion from or delivery from supply to demand to the final energy service. However, we have to understand that our energy system is embedded in our economy and also a part of the environment. So that means we have to understand the environmental, economic, and social impacts of our energy system, as you can see on the top of the chart. But I want to highlight the environmental and health impacts as we discuss in this session. Those environmental impacts include air pollution, and air pollution create a human health impact. Water consumption, we will talk. Land use impact, we will talk a little bit, but if you're interested, it's another area for future research. Ecosystem, those in addition to land use, it can create impacts to animals, for example, birds and other impacts. And in addition to land use, you can vegetation and soil and other ecosystem impacts. Climate change, we will dedicate another session to discuss more climate change because it's a huge topic. So what are the examples of energy-related air pollution? Here you can see the pictures summarize the different sources of energy-related air pollution. This is from IEA, and power plants is very typical, and power plants is point sources that, or stationary sources, because it's stay there and it has it's a big source, and it's very often we need to focus on those stationary sources. It's not just because it accounts a big portion of the pollutants, but also if we pay attention, we can achieve the mitigation at sufficiently more effectively and at a lower cost. Particularly coal power plants, oil power plants, gas power plants have some air pollutants, but much less than coal and oil. And that's why the transition from coal to natural gas saves air pollution, reduce air pollution. Natural gas has minimum soft LOX pollutions, but it still has carbon emissions if we take carbon emission as pollutions too. And on average, per kilowatt hour of carbon emission from natural gas plants is about half of those from coal plants. Moving point sources, automobile, road transport, trucks, cars, if not regulated, they are very big part of the air pollution. If you pay attention to the whole discussion or history of air pollution regulation, it was partly pushed by the severe air pollution in big cities such as Los Angeles, New York City, when in the 60s, 70s, that everybody trying to drive automobile, and at that time, air pollution from automobile was not regulated, and that created a huge problem of air pollution. And now it's getting better, but still it's still a very important source. A third example is the residential use of fossil fuel and the bioenergy, especially in the developing world, where the residents or families still using biomass as their source of energy for cooking or heating. And the particular matters from emissions from biomass burning is a big source of the indoor air pollution. And very often women and the kids that do the cooking or collecting wood, that create another layer of inequality or justice, that gender inequality in the energy supply or energy consumption. That's another area for research. We'll talk a little bit in the energy access discussion. Industry combustion or industry processes. This is so-called hard to abate, hard to mitigate sectors. Some industry is very hard to electrify, especially iron, steel, or glass industries that require high temperature and very often hard to achieve through electric furnace and still burning metallurgical coal, and this is an area for active research too. In countries like China, because it has manufacturing basis, and it's also the center for heavy industry, and industry sources is especially a big portion of the pollutants. What other hard to mitigate area is the non-road transport, especially airplanes, ships, and trains. Trains better because it's now highly electrified, but airplanes, international cargo ships, still burning diesel, or it's an area that very hard to mitigate. And this chart shows the black air pollutants that come from a cargo ship. That's it's an example. Other sector energy related pollution come from the mining, the transport of energy, for example, coal. The mining of a coal create dust and they create environmental ecosystem degradation, and the transport of a coal also has the particular matters and dust and other create other air pollutants. So the whole system, as you can see here, has emissions, has ecosystem problems, and create socioeconomic challenges, as you can see here. That's why we take the environmental consequences of energy system as a big concern. And when we study or simulate energy system, this also becomes a constraint that we need to address, especially if we take, because governments set up very ambitious goals for air pollution reduction and carbon mitigations. And those targets becomes the constraint of how can we design or operate our energy system. And that's where we need to really integrate those constraints in our analysis. This chart covers the different air pollutants and where they come from, and how big contribution are from our energy system. As you can see here, sulfur dioxide, nitrogen oxide, 99% of sources are from energy sector. Power sector are a very important contribution of sulfur dioxide. Probably transport is the largest contributor for nitrogen oxides, and building sector is the largest contributor of particulate matters, in addition to industry and the power sector. Carbon monoxide, where mostly come from building sector and transport sector, and we'll see volatile organic compound mostly come from building sector, transport sector, and ammonia. Only 3% come from energy sector, mostly come from agriculture and waste sectors. So this chart visualizes very lively. So what are the pollutants, main pollutants, where those pollutants come from, and how different sectors contribute to those sectors. So if we talk about particular air pollutants, we can see, or we can discuss where should we focus and what can we do it? And this kind of flow chart, just like the energy flow chart, now this is the pollution flow chart, can help us to understand where the problems are. This chart is very important. I cannot emphasize more or emphasize enough the logic and the flow of energy, environment, and human health analysis, because it provides a system analytic framework how we approach those kind of problems. First is causes. From building sector, industry sector, transport sector, right? That's what the previous chart shows. And that are the sources related to human energy activities, for example, power plants, industry, households, transport, agriculture, waste management, waste treatment. It also has natural sources such as volcanoes, wildfires, dust storms, sea salt sprays contribute to the different air pollution we were talking about. And those sources and come out in the form of emissions, different pollutants, right? So primary pollutants such as nitrogen oxides, sulfur oxides, particulate matter, carbon monoxide, black carbon, ammonia, VOC, those are the main pollutants we already can add. If we see carbon as a pollutant, we can add a carbon to it, but carbon has different problems that creates the climate change. It's different, but it's still important that we will talk separately. And different air pollutants, they have different chemical formula and mix together. Some can have chemical transformation and create the so-called secondary pollutants through mix and secondary chemical transformation, and or react with other contributions or react with each other, create secondary particulate matter, ozone, depleting chemicals, sulfuric acid, nitric acid. And so those chemicals or secondary chemicals, and they dispersion and concentration that's into the air, where mixed in the air, and that's what human breathe. And so the population get exposed to the concentration of the air pollutants, and that create a health impact, especially for the vulnerability population, kids, old people, and or people with certain kind of disease that's vulnerable to or sensitive to air pollution. So factors influencing dispersion and concentration, for sure, first is the volume, location of the emissions. If it's nearby the population center, then it creates a large problem. If it's far away, the environmental carrying capacity can digest or can really help to address those air pollutants. That's might not a big problem. That's also where the environmental justice come into play, because very often the power plants or air pollutions create a burden for people who live nearby those emission sources, and very often those are underdeveloped, underserved, disadvantaged communities, and we need to address the disproportional impact to those populations. Fixed point mobile sources. I mentioned power plants are more stationary, while automobile are mobile sources. Mobile sources, which means they are harder to address because they keep moving. While stationary sources, we can use in technologies and to address emissions more effectively. Whether capacity to contribute to secondary pollution, topography, and those are important factors. And even wind can contribute. When wind blows, they blow away the the air pollutants, and that's why air pollution in big cities very often connected to those all the different factors. And the effects of air pollution concentration as impact to human health. I mentioned different population groups may have different effects. But as you can see here, it creates heart or lung diseases. It creates acidification and eutrophication of water and soil. It damaged crops. It creates climate change, and it also creates damages to culture sites and biodiversity. If we talk about acidification, and sometimes air pollution reduces visibility, which creates problems of more traffic and accidents, and also impact human psychology because you may not feel happy when you see severe air pollution. So this provides a framework from sources to exposure that human health impact or environmental impact, and it's for the researcher or for the system is really to establish the source explosion damage function, and for different population, for different location, and how different factors contributed to the concentration and the explosion. If you look into the literature, those are the keywords or information that we need to get in order to do the analysis. And because this is all evolving, control technology and human, even for households, they can use air filter to improve the indoor air quality. So some of the impacts may harder to quantify, but as new data come in, and it provides some very influential work that you can see from news and from research. This is a very important chart. I hope you really pay attention and really understand the different linkages. One particular important pollutants is the particulate matter emissions. These also come from the IEA report. I posted 2 IEA reports. One talk about air pollution, one talk about water consumption, energy water, nexus. Both are IEA reports, and both are very good, very comprehensive. From today's perspective, it may seem a little bit out of date, but still that's the most comprehensive analysis that we can find. I highly recommend to read through the chapters that you find interesting. This one shows where the PM emissions come from by sector and region. As you can see here, China, India, Africa, where PM pollutions are still big problems there, and building sector, industry sector, and the transport sector are the large sources of the PM pollution. PM pollution, especially PM 2.5, the fine particle matters, really damage human health and create all sorts of problems. And that's where the new frontier for air pollution mitigation, because we have better technology to address sulfur and LOX and those traditional air pollutants, but particulate matters are much harder to regulate. In order to regulate or handle air pollution, different countries create the air pollution standards, AQI. To, as you can see here, EU has probably the highest standard. US, China as very comparable, just different name. While India, Indonesia, comparatively looser standards, but for the definition of good, it's really collected to the World Health Organization, what really contributed to human health impact. That's also why when we see this similar reports of AQI, and different locations might respond, different population might respond differently, because good quality in United States, China, India might seem not very good in European standard. And the WHO recommends 20 to 25 microgram per cubic meter, and that's same as health. That's no impact, and if it's larger than 100, then it becomes unhealthy and polluted in most parts of the world. And if you remember your first assignment, some days Beijing or New Delhi, the AQI reading out by more than 500, even approaching 1,000. That's how severe the air pollution in those days are. And pay attention to how AQI is defined and used that way, because that's the data input very often for your analysis. We will use power plant, for example, to show how power plant, as we mentioned, it is a stationary source, and we now have more standardized technologies to control the different air pollutions. For example, from the source, power plant, we are trying to use low sulfur coal or coal blending, different quality, to blend with higher quality, and that will reduce the emissions from the source. And if the coal has high sulfur rate, then it needs to be washed, to wash the sulfur and the ashes away. So it more efficient to burn those coal and less pollutants. Mercury control, different methods, light drain oxides and LOX control. It's in during combustion or post-combustion using technologies such as selective catalytic reduction or non-catalytic reduction, some chemical, physical methods, particulate control using filters and other ways, including black carbon and even filters and electrostatic precipitators that can absorb those particular matters. FGD, that's a way to control sulfur dioxide. Wet scrubbers, spray dry absorbers, seawater FGD, and it's a effective way to reduce emissions of sulfur dioxide. And sometimes particulate matter or FGD are integrated, and in developed countries, soft mercury control is included, but in developing world, still focus more on sulfur and LOX, and not even particulate matters, depends where you are, because each step it adds cost, and the priority will often give to the most severe impact ones that are still the conventional pollutants. So that said, you have reduced it from the sources, so you have higher efficient combustion and less pollutants, and then the post-combustion, the pipe end or stack, chimney end treatment. The different technologies can provide efficiency here, as you can see here for particulate matters. It can achieve 99% reduction. That means for power plant, you can really make a huge difference to introduce the technologies that reduce the pollution. Sulfur and LOX, depends what technology you use. It can reduce between 90% and some are less efficient, 20%, but if you different mixed technologies still, this is doable. It adds some costs, but the benefits overweight the costs. And there are many research on that, and it depends on how you value the human health impact, really. So air pollution really contribute to premature mortality. This study shows where you have higher air pollution concentration, the impact to mortality or human health also much larger, as you can see here. China, India, South Asia, Central Africa, and Eastern Europe, even Eastern US are more exposed to air pollution. Therefore, the observed mortality, premature mortality rate is also higher. That's exactly shows the human health impact of air pollution. One other aspect of this, which is less discussed and should be considered, is how trade contribute to air pollution and the inequality in the global system. That let's say a product manufactured in the developing world, so the energy consumption in the developing world and air pollution left in the developed world, while the products might have consumed in the West countries. So who should bear the costs of air pollution? So these papers using the trade data to adjust what if they should count, the consumers should count the impact. So what if the products are manufactured in their country? Then you would observe the sulfur dioxide emissions increase in the Western countries, and PM 2.5 exposure increase in those countries, and increase of premature mortality in those countries. So this create another layer of thought-provoking sorts. How should we discuss the inequality in the international trade, and who should bear the costs of air pollution that embedded in the international trade? Similar questions can be discussed in water, and so let's bring up our next topic is the water impact of our energy system. This from the IEA water energy nexus, or energy water nexus, that energy sector accounts about 1/8 of global water withdrawal. As other countries, agriculture is still the largest or primary source of water demand, but energy sector is a very important contributor, especially power generation. Here we need to differentiate water withdrawal versus water consumption. Withdrawal is the volume of water removed from a source, that how much water we withdraw from river, from lakes, from ocean. And consumption is the volume of water that is not returned to the source. Let's say we withdraw water from the river, then after cooling the power plant, we destroy the warm water, we discharge the warm water back to the river. So that part is not consumed. So as you can imagine, water withdrawal is larger than water consumption, right? And the discharge of the volume of water returned to the source, that very often has an impact, because it may degraded by usage, unearthed physically or chemically, sometimes have pollution, sometimes adding temperature, and that impact water quality. And if it's warm water back to the river, it creates a thermal pollution that fishery or other water ecosystem would impact. Water withdrawal is usually larger or equal to consumption. If water is constrained or water resources limited, then it's very important to reduce the consumption. That's why at the beginning we mentioned the potential for energy, water saving in our energy systems. So we focus on differences by technology. Let's say water withdrawal or water consumptions, and it's the consumption that we really consuming water, but the withdrawal, even with discharge back to the system, still we need to try to reduce the impact. Different technologies has different water footprint. No matter you're talking about water withdrawal or water consumption. And as you can see here, renewables compared to fossil fuel power plants, it's significantly reduced the water footprint. This also shows water consumption is usually less than water withdrawal. So it may interest why renewables still has water consumptions, mostly due to the fact that cleaning services for solar PV and CSP. CSP need the water for its because CSP heat the water and create steam. It still consumes a certain amount of water, and solar PV need water to clean the panel that consumes some water. For other plants, mostly during the steam turbine, you need a steam, and steam evaporates, and also during the cooling process, and that consumes water. So that brings the topic that the different cooling system, as you can see here, it highlights 4 technologies. One through is, as you can see from the name, right? You withdraw the water from the river or other sources. It flows once through the system, cooling down the system, and discharge back to the water system. And it has the highest water withdrawal, as you can see here, per megawatt hour basis. And then cooling plant that you can, the water is discharged not back to the river, but back to a cooling pond. After the water cooling down, you can use the cooled water to cooling the plants. So as you can see, this reduced the water withdrawal. And then they recirculating, that the water is recirculating in the system, and that add more evaporation. So you can see water consumptions per megawatt hour increase, but what it's reduced very much the water withdrawal. Depends what you see from. If you have more than enough water, then you might use one through, or if you have water constraints, then at least you try to recycle or recirculate the water. And more if water is limited, and the power plants can use dry cooling to cool the power plants. That try to create the dry cooling technology, basically using the air, the tower create a physics that because warm air, hot air always moving up, right? And that the fresh air, cooling air flows through this chimney and bring down the temperature. So dry cooling saves water and barely consume any water. And but still you have steam turbine. The turbine still consumes water. It's reduced the water during the cooling process. And but it has energy efficiency penalty. Where often the efficiency, you will get a slightly lower efficiency for the power plants, because especially when the temperature is high, because it's not as quickly as efficiently of cooling compared to water cooling plants. So energy, water, carbon emission, human health, this create an area for nexus research. And this is an example of my co-authors and I work together to study the trade-offs, the linkages between the different impact factors. And there are a couple of messages where we use China's power system as example, and we studied the impact of lower cost of renewables and introduce water constraints in the power system. We see with lower cost of renewables, it reduce the need for carbon capture and sequestration in the system to deliver carbon neutrality goals, to reduce the carbon emissions. And if we add water constraint to it, because CCS, carbon capture and sequestration, still use water. And if water is a constraint, that almost completely kick it out the need for CCS. So that adds the discussions that if we have cheap renewables, if we have water constraints, we don't need CCS. It's not feasible for CCS to really play a role. So those technology implications of our system is very important when we think about today's investment to achieve carbon neutrality, and to understand the different dynamics between technologies and the future pathways. One other area is the impact is the land use impact. So when we have our energy projects, it takes land. Power plants, solar PV farms, wind farms, and conventional plants, they all take lands, right? And they all have emissions per terawatt or kilowatt hour basis. If with these two is our focus, then we can plot their impact by technology. As you can see here, land use, it's different. And for comparing the different sources, you can see here biomass takes land more, probably highest, because you need to grow the vegetation or material that you can use in the biomass plants. And the greenhouse gas is mostly the fossil plants such as coal plants and oil and natural gas plants, and nuclear, which has probably lower footprint, carbon footprint, and land use footprint. Integrate PV, because it's integrated to the building, it doesn't take extra land, but solar PV, solar CSP, it's still the ground-mounted PV still take lands. The land use impact you would need, but those land can have multiple usage. I will explain that later. Is the concept of a co-benefits. The integrated solar PV integrate to already existing infrastructures such as building, rooftop, it doesn't take extra land, or airports, commercial buildings. And this one example is on the canal in California as a concept that using the open space of the canal to build the solar panel, and which generate electricity, and the cover also reduce the evaporation, and that saves water. So it has multiple benefits. Examples like that, and integrate solar PV with agricultural land. Sometimes this can create ecosystem benefits because it creates shade, and shade helps reduce evaporation. And when you do cleaning, and the water can help the restoration of the ecosystem. So those are some of the co-benefits. And for development of our energy system, we need to think about more of those co-benefits. And floating solar, which is another example that you build in solar on waters, and to try to reduce the water evaporation, and at the same time generating electricity. Those are very good examples of co-benefits and energy water nexus. To sum up, environmental and health impacts are the external impacts of energy systems, and that's also where human society really pay attention, because we want to reduce those impacts. And the regulation or the mitigation goals, carbon mitigation targets, create constraints that to design and operate our energy system. That's where energy system modeling see environmental and health impacts as the constraint of the energy system, and that would impact how we invest today's technology. I mentioned the energy, air pollution, and human health framework for analysis to try to find the right concentration and exposure functions that you can use, and think about the benefits in the energy, water, carbon nexus discussions. Those will help us to understand this session. Here are some further references in addition to the two IEA reports. If you're interested, those papers can provide a very good reference for you to get a big picture of some of these topics. That's all for this session. Thank you.